roll before I started, but it's pretty hard to do. Okay. And we'll go from current slide as soon as the projector gets turned on. And I did give you the second test in this last time, right? Yeah. Okay. All right. Corey wasn't here for it, so hopefully he'll show up sometime to pick that up. Okay. So we finished Chapter 2. Chapter 3 was on modeling with linear systems, first-order differential equations. And that's some good stuff there. It really is. But nothing in our course description said anything about modeling. So we got other things we need to hit, so we're going to hit those. If we run out of subject matter before we run out of term, which is not very likely, then we'll come back and pick up some of the modeling applications. Okay, so Chapter 4, beginning on page 118, is higher order differential equations. Okay? What we did in Chapter 2 was strictly first order differential equations. And we did a variety of things there. 4.1 is going to talk about the preliminary theory linear equations, okay? And then we'll deal with some other things later. And again, this is a little bit one of those that they play around the edges of things, is how I look at it, and talk about different principles that later we'll come back and tie them together better, okay? That's probably a nebulous way of describing it, but it's the only way I can put this together, okay? 4.2, reduction of order, is very short section, just does two examples, a couple things there. And then we start in 4.3, what I think is the real meat of this, sort of like Chapter 2 had sort of a nebulous 2.1, and I don't remember if 2.2 or not. At some point we started actually doing it. Same thing here, we're going to play around with nomenclature, the edges and stuff like this, and then about 4.3 we'll get going on really doing this. So, first, Chapter 2, we're able to solve a few first-order differential equations, recognizing them as either separable, linear, exact, having homogeneous coefficients. Now that's what they're calling those, homogeneous coefficients. Probably would have been a good idea to call that from the beginning. Okay? We did a few others, Bernoulli and some other things like this, but yeah, that was mostly what we were after. Even though the solutions obtained were in the form of a one-parameter family, that family, with one exception, did not represent the general solution of the differential equations. So now, here's the nomenclature. This is the verbiage here. The general solution is a family of solutions defined on some interval I that contains all the solutions of the differential equations that are defined on I. Boy, does that sound like a redundant sentence, okay? Only in the case of linear first-order differential equations were we able to obtain general solutions by paying close attention to certain continuity conditions imposed blah, 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 blah. Okay, so let's start with 4.1.1. Initial value problems and boundary value problems. I think I've mentioned boundary value before, but I believe this is the first time the book is really addressing it. So back in section 1.2, we defined an initial value problem for the general nth order differential equations. Nth order. There we were being very general with things. Okay? For a linear differential equation of nth order initial value problem, here's what this equation looks like, the differential equations. Okay, let me get my pen set up. Now, some of this hopefully will be a little familiar because we've kind of talked around it before, but a linear differential, nth order differential equation. A sub n of x. Okay, now that looks a lot like maybe what we've done in other things. We'll come back and make some comparison. dny dx to the nth. Okay, plus a sub n minus 1 of x d n minus 1 y, and these dx to the n minus 1. I tend to like to put parentheses around those, but he doesn't, so I'm not going to do it. Okay, plus dot dot dot. We keep stepping down, and here's what I was sort of making a reference to. Way back in polynomial expressions, we use an a sub n to represent the coefficient, not a function of x, just the coefficient, a sub n. And I hope that someone said along the way, or you picked up along the way, the n here is just a marker for here. It's just a marker saying this is the coefficient that went with x to the nth power. That was for a polynomial. Okay? When you had x to the n, that n was part of the problem. That was the nth. That was power n. X raised to the nth power. X of x, yeah. So that was part of the problem. This n was just a marker saying this is the coefficient that goes with that term. Well, the same type thing is happening here. This is some coefficient function of x, because you're taking derivatives with respect to x, so you can have this here. You can't have a y in here, otherwise it wouldn't be linear, okay? But it can be of x. But this is just saying this is the coefficient function that goes with this derivative. Now it's not powers, these are derivatives, okay? In a polynomial function, we call it nth degree. In a differential equation, we call it nth order, okay? So this is that to the nth order. This is the polynomial function that goes with this derivative, the n minus first derivative. And you count your way down in those derivatives till you get down to a sub 1 dy dx, because that's your first derivative, plus a sub 0, I forgot to put my of x in here, a sub 0 of x times y, and that's equal to some g of x. Okay? Now if you remember, first order, this is all we had. Okay? We had a sub 1 of x dy dx plus a sub 0 of x times y equals some g of x. And then what we did to do it, divide by a1 of x, because that couldn't be 0. It can't be 0, because if that was 0, this wouldn't be a differential equation, would it? This would be, this is equal to, yeah, so obviously this can't be 0. So we divided by that, and then we had it in the form p of x, blah, blah, blah. And we proceeded from there. So now we've just strung this out and had it nth order. Notice none of these terms, this term, these coefficients, can have anything to do with y or any derivative of y. And all these y's and derivatives can't be multiplied by any. And they can't be raised to any power other than 1. That's what makes it a linear, nth order differential equation. Okay. Now, that's the most general form for that. Now, for this to be an initial value problem, remember before when it was a first order differential equation, you only had one initial condition. Now you need an initial condition for every term, let me say it this way, for every degree of that differential equation. Okay? Well, not degree. Order of that differential equation. You won't have one for this derivative, but you'll have one for each order. Because this is the zeroth order, okay? So we'll have a y, we'll have a y prime, we'll have a y double prime, y triple prime, all the way up to this one. We won't have one for this one, but we'll have one for every one up to that. But if you think about it, 0, 1, 2, 3, 4, up to n minus 1, that would be your nth one, because it's one more than the number there. Okay. So here you're subject to are your initial conditions. Y of x0 is equal to y0. Okay? Y prime of x0 is equal to y sub 1. Dot, 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 until you get to y to the n minus second at x sub 0 is equal to y, okay, let's get them counted off right, to the n minus 3, I believe it is. They don't, no, n minus 1. Okay. No, n minus 2. Okay. This is, yeah, this is 0, 1, 2, 3, 4, up to yeah, that's right, I believe, comma y sub n minus 1 at x0 is equal to y to the n minus 1. Okay. You have 0, 1, 2, so you have n of these. You have nth order up here, you have n initial conditions. But you only count to the n minus 1 because you see this one would be 1, 2, 3, 4, 5. That gets you up to n minus 1, but your 0 is your nth one. Okay. Now,
all these must be defined at the same point.
That's exactly what I was going to say. For an initial condition, it has to be at the same x value every one of them. Every one of them. Okay? For an initial value problem. Now, there's a part of me that wants to call it something other than initial, because it doesn't have to be the first value. That's what initial means to me. But it means a single value problem. You know, in other words, at some single value of x, every one of them has to be there. Okay? That's what makes what they call an initial value problem. Okay. Now, you always have to be defined on some interval, I, that contains this x0. Otherwise, it doesn't make any sense. Okay? And it has to satisfy the differential equation. It has to satisfy every one of those initial conditions. Okay? N of those initial conditions. Now, next thing they talk about is existence and uniqueness. Back in section 1.2, we stated a theorem that gave the conditions under which existence and uniqueness of a solution of a first-order initial value problem were guaranteed. That theorem, the theorem that follows here, gives the sufficient conditions for existence of a unique solution of this problem, the one I've got written here. So here's what that is. This is theorem 4.1.1, existence of a unique solution. Let your a sub n of x, a sub n minus 1 of x, a sub n minus 2 of x, dot, 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 all the way down to a sub 1 of x, a sub 0 of x. Okay? And your g of x. So those are all those coefficient functions plus your function of x on the other side of the equality. Okay? Let all of them be continuous. Okay. Can't have any piecewise defined functions there. Okay? They all have to be continuous on an interval I. Okay? And let a sub n of x not equal 0. Okay? Now this is the same type of thing we have with a polynomial function of degree n. That a sub n can't be 0, because if it was, then you have a polynomial of degree n minus 1. Well, same thing here. This a sub n of x can't be 0. That otherwise, if a sub n of x was 0, then this term would make no sense. That wouldn't have any meaning, because that's 0. So then you'd have a differential equation of degree n minus 1. So for this to be degree n, the a sub n can't be 0. Okay. There's nothing else about it. It's just it won't be a nth order differential equation then. Okay. And that has to be for every x in the interval. Okay, none of those a sub n for any of the x's in the interval can be 0. Okay. Now, if x is equal to x0, those are our initial conditions, is any point in the interval, okay, then a solution y of x of this problem, of the IVP, initial value problem 1, that one right up there, exists on the interval. Okay? And not only does it exist, is unique. Okay. So that's what it takes. Every one of those coefficient functions and the g function have to be continuous on the interval I. The a sub n can't be 0 anywhere in that interval I. And the x equal x0 is in I. And if all those things are met, and they actually say it a little bit stronger than me, if x equal x0 is a point in this interval, okay, that's what it is, then the y of x of that initial value problem exists and is on I and is unique. Okay. So here's example 1. All right, to erase? Well, I'll let you finish writing. Okay. Here's an initial value problem. 3y triple prime plus 5y double prime minus y prime plus 7y is equal to 0, where y of 1 is equal to 0, y prime of 1 is equal to 0, and y double prime, okay, is equal to 0. Now, don't think they all have to be this way, okay? They don't. They just happen to pick this one. But notice this is a third order differential equation, and you have 1, 2, 3 initial conditions, okay? Initial conditions all have to be at the same point here. They do not have to have the same values there. These just happen they do. It's immaterial that they do, okay? But they have to have the same x value in the parentheses, okay? So there's our problem. All right. Here, all your functions of x's are constant functions. All your coefficients are constant, and your g of x is not only a constant, it's 0. Okay? It's a pretty simple thing. Okay? Now, this initial value problem, if you think about it, okay, the trivial solution solves it, doesn't it? Trivial solution being y is equal to 0. Right? If y is equal to 0, y prime is equal to 0, y double prime is equal to 0, y triple prime is equal to 0, and all those things multiplied by whatever they're multiplied by, added together, subtracted, whatever, they're going to equal 0. And y of 1 is going to be 0, y of 2 is going, y prime of 1 is going to be 0, and y double prime of 1 is going to be 0. Yes, that is a solution. And because it's a solution, and it meets all the requirements, that's the only solution. That's a unique solution. Okay? Because the third order differential equation is linear, with constant coefficients, follows that all the conditions of 4.1.1 are fulfilled. Therefore, since this is a solution, it has to be the only solution on any interval that contains x equal 1. You can't have any more, okay? Oh, it's not very exciting, is it? You know, your trivial.
Give us a bunch of these.
What's that?
I said, give us a bunch of these.
Okay. All right. Well, let's see if example 2 is like that. I have a feeling it's not. This is on the next page. Okay. Now this is one of those you should verify. They don't tell you how they get it, they just say you should verify. You should verify that this function, y is equal to 3e to the 2x plus e to the minus 2x minus 3x is a solution of this IVP, initial value problem, y triple prime minus, I'm sorry, that's a double prime, I'm not seeing well right now. Okay, y double prime minus 4y is equal to 12x. Okay, subject to, how many initial conditions do you need? 2, absolutely. Y of 0, this time it's starting at 0, is equal to 4, but this value is not 0. And y prime of 1, y prime of 0, has to be at the same value, 0, but it doesn't have to have the same value here. This one happens to be 1. Okay. Now, again, that is a linear differential equation. Your primes, your y's only exist by themselves in any term, and the coefficients are all functions of x. They happen to be constants in this case, and the one at the other side is a function of x. And your initial conditions are at the same point, so they are initial conditions. You have to have 2 of them because it's second order. Now, we need to verify this is a solution to that. How do we go about verifying? Take a derivative, right. Y prime is equal to? 6 e to the 2x.
Times 2.
Second?
Times 2.
Times 2? Is that what you said?
Yeah.
Or minus 2? Minus 2.
Minus up there.
Okay.
What's that? What's the first term up there? That's a plus.
Okay, it's a plus here.
No, I'm saying e to the 2x.
E to, yeah, 3e to the 2x.
E of 2x. Oh, I've already done that.
Yeah, you already did it. Yeah, okay, yeah. You already did the times 2. Continue.
Minus 3.
Okay, you got minus 2x, right? Minus 3. Perfect. There's your y prime. We also need y double prime. Oh, the 10 o'clock scholar. Good. Okay.
Well, I can't study. Go back to work.
Well, we want you to pay your bills, especially if it's to the school. Okay.
I'd like them to not get shut down or anything.
Oh my goodness, he's giving me a book. I deserve it, huh?
Well, I had a few choice words for you on a couple of them. So,
My ears were ringing all night. Okay. Twice in 2 different tones. Okay. Maybe 3. Okay. Yeah, you can do that. Oh, I get you marked here on that.
well, thanks, I guess.
Whatever that difference that makes.
I don't think it does, but
Yeah.
maybe it'll help one day.
No one pays any attention to it. It's just they make us do it. So.
Y'all have a good weekend.
Okay, work hard.
Thank you.
Okay. All right, we need to do y double prime too, because we have a y double prime over there. So what do you have for that? 12 e to the 2x
Minus, plus 4.
plus 4
E to 2x.
minus 2x, right? And that's it. Okay? Now, let's plug in to your differential equation what we've just discovered. Y double prime is 12 e to the 2x plus 4 e to the minus 2x. Minus 4 times y. So I don't need to do that y prime anywhere. I just needed to do it so we could get y double prime. So if it's okay with you, I'll just multiply by minus 4 by everything up there in y. So that would be minus 4 times 3 is minus 12 e to the 2x, right? And then minus 4 times 1 is minus 4 e to the minus 2x. And then minus 4 times minus 3x would be plus 12x equal 12x. Okay? I believe that's going to bounce out pretty well. 12 e to the 2x minus 12 e to the 2x goes to 0. 4 e to the minus 2x minus 4 e to the minus 2x goes to 0. And 12x is equal to 12x. Okay? Now, I don't see any real place that we, well, yeah, okay. To fit the initial conditions, go back to your y. So y of 0 is equal to 3. E to the 0 is?
E to the 0.
Yeah, 1. So that would be 3 plus e to the minus 0 is 1. So that's 1 minus 0. Okay? So that's equal to 4. And sure enough, y to the 0 is 4. Okay, let's do it. Now we use our y prime. Y prime of 0 is equal to 6 times e to the 0, which is 6, minus 2 times e to the 0, which is minus 2, which is 1, makes it minus 2, minus 3, and that would be 4 minus 3 is 1, and that fits too. So both of our initial conditions fit, your differential equation fit, everything fit. So sure enough, that was a solution. In fact, the solution. Well, I don't know. Notice they say is a solution of the initial value problem. You would think with the theorem, it would be the solution, the one and only solution. Let's see if they say anything about that. Oh, and where is it the solution? Well, there are absolutely no restrictions on anything here. E's are good everywhere. You don't have any problems anywhere, so this should be good on minus infinity to infinity. All real numbers. Any interval that contains 0. Okay.
So if we shortcut and say that, but normally, do they want the largest interval possible?
In general, you do. But most of the time, if there are restrictions, they're pretty obvious where they are. And then you usually say from here to here. You know, if there are restrictions there, or from here to there, or from here, out there to here, you know. Usually you give the entire thing. But if, for instance, there's a physical situation, so say you're talking about the radii of a camshaft or something like that, and you know they can't be 0, then even though the equation says from minus infinity to infinity, you know it can't be minus infinity, so you put down what makes sense. Okay. I just made up the camshaft because it sounded good. But okay. And it says it's on that for choice of any parameter C. I never saw the parameter C anywhere in the... Oh, yeah, I'm sorry. Okay. I hadn't read well enough. Okay. I skipped down too far. The requirements of theorem 4.1.1 that all your a sub x's from I to n be continuous, and the a sub n of x cannot be 0 for any x in the interval, are both important. Specifically, if a sub n of x is equal to 0 for some x in the interval, then the solution of the linear initial value problem may not be unique or even exist. For example, and here's another one they said you should verify. So I'm going to go to a clean page here. Okay? You got what you need here?
Yeah.
Okay. All right. Here's one. Y is equal to cx squared plus x plus 3. Okay? You need to verify that is a solution for this initial value problem. Okay? X squared y double prime minus 2xy prime plus 2y is equal to 6, I believe it is, with the initial conditions that y of 0, oh boy, is equal to 3, and y prime of 0 is equal to 1. Okay. Now that may look well and good, doesn't it? That looks like a perfectly reasonable solution. And it seems like a perfectly reasonable differential equation with very nondescript initial conditions. They're both at the same point, everything's good. Does anything seem like it might smell a little bit to you? Not yet?
Zero, 3, 0, 1. It's at the same point, so.
The second order differential equation, you got 2 initial conditions, that look good. Here is a big problem. We'll see it. We need to verify this is the solution for that differential equation. So we're going to need to do y prime, yep, will be,
2xc plus.
second,
We're
2,
gonna write 2xc
2cx plus 1. That's enough. Then y double prime is equal to 2c. Done. All right, let's go back and plug in. This would be x squared, or 2cx squared. Is that okay? Okay. Minus, we got to multiply minus 2x times this whole y1, so that would be minus 4cx minus 2cx squared minus 2x. Right? The minus 2x times y prime would be minus 4cx squared minus 2x. Okay? Plus 2y. Your y is this, so that would be plus 2cx squared plus 2x plus 6. And supposedly that should equal 6. Let's see if it does. Here's 2cx squared, another 2cx squared, those add to 4cx squared, minus 4cx squared, that adds to 0, minus 2x plus 2x, that adds to 0, 6 is equal to 6. Sure checks on the differential equation part. Let's check your initial conditions. Okay? Y of 0, so y of 0 is equal to 0 plus 0 plus 3. And that's equal to 3. That checks. Okay? Now let's do your y prime. Y prime of 0 is equal to 0 plus 1. And that's equal to 1. That checks. Everything looks good. Now, I've got a big problem here. This is a unique solution, because you can plug in any value for C you want to, and this will still work. So how have we gone wrong? Okay.
We said a solution, didn't we?
The what?
Oh, we said a solution.
It is a solution, but remember the theorem said it should be a unique solution. Here's the problem. What is your x designated here? 0. What if you put an x equals 0 here? Oops. Your a sub n cannot equal 0. Now, if you had anything else here that worked, then you just exclude that from here. But you see, that's part of the problem here. You're saying x is equal to 0. It can't be 0, because that would make the leading coefficient 0. It can't be 0, because then it wouldn't even be a second order differential equation. So this is.
And then again, if you put x in the second one, that would screw it up too.
It would definitely. That would say 2y is equal to 6, x equals 3, y is equal to 3 is your only solution. That's it. You know, there aren't any solutions to this thing. Okay? So, and y is equal to 3, that would be when x equals 0. Okay? So, no. That's the problem. Okay? And here it is. Y is x equals 0 is equal to 3. Yeah. It's just that y prime would not be 1. Y prime would be 0. Okay, because y is equal to 3 is the only. I mean, it's. Well, I guess, yeah, okay. So that's the issue. You can't let something sneak in there like that that'll mess up everything. Those conditions are important, that all your a sub x's have to be continuous, and your g of x is continuous. In this case, they work. No problem there. But that thing about the n of x cannot be 0 for any value in the interval. And yet you turn around and said y at 0 is that blew the whole problem right there. Okay. All right. Their statement, although most of the conditions of theorem 4.1.1 are satisfied, the obvious difficulty is that it's 0, x equals 0, and the initial conditions are imposed that x equals 0. Can't happen. All right. That was sort of tricky. All right. Now we're going to address boundary value problems. Okay? Another type of problem consists of solving linear differential equation of order 2 or greater in which the dependent variable y or its derivatives are specified at different points. Okay? So here would be a situation like that. A sub 2 of x, so this is going to be a second order differential equation, d2y dx squared plus a sub 1 of x dy dx plus a sub 0 of x y is equal to sum g of x. That's your generic overall catch-all second order linear differential equation. Okay? But that's your equation. Here's your subject to. Y of A is equal to y0, and y prime of A is equal to y1. Oops, sorry. That was an initial value problem. I got carried away there. Y of B is equal to y1. Okay? Now, this is called the boundary value problem. You have a bound on one end and a bound on the other end. So it's called the boundary value problem. Initial value problem, you only have information at one end. Here you have information at two ends. Okay? And generally you are limited to two. Okay? It really gets weird if you have three or more, but two. But those two values are not the same. A is not equal to B. Obviously, if A were equal to B, then y1, y0 would have to be y1. Otherwise, it would be a function. You have two different values at the same time. That can't happen. Okay? So these have to be at two different points. Okay. Now, goodness, my nose itches. We must be going to have company. Okay. This is called the boundary value problem, and we often refer to this as the BVP as opposed to the IVP, boundary value problem. Okay? And these things over here are called the boundary conditions, whereas when you have initial value problems, they're called the initial conditions. Even though they may not be at the beginning, they're still called the initial conditions. So a solution for the foregoing problem is a function satisfying the differential equations at these 2 points, A, y0, and B, y1. Okay? And that's what they're talking about here. Now, I don't find this particular figure all that instructive, but I guess it can be. Every one of these lines are supposedly solutions for this equation. Okay? That works, this works, this works, all these work. However, these two happen to fit the bill for A y0 and B y1. See, the A and the B are two different points on the x-axis, but the y0 and y1 are different points of the y-axis. So you could have two or an infinite number of solutions that meet at those 2 points, and they won't be a unique solution, okay? Because you could have 2 or more solutions that fit both of those requirements, okay? Now, those are not the only 2 boundary conditions you could have. Here's another set of boundary conditions you could have had. And it doesn't matter on the order of these. I would tend to do this. Y of A is equal to, and they're still using y0, and y prime of B is equal to y1. That would work just as well, okay? You still won't have unique solutions. Or you could use y prime of A equal y0 and y of B equal y1. That would be legitimate boundary value problems conditions as well. Or you could have y prime of A equal y0, y prime of B is equal to y1. All those are legitimate boundary conditions. None of them will produce a unique solution. Initial value problems, they will. But boundary value problems, they will not. Okay? So you're...
Well, why not?
What's that?
Why not? We don't give them why they won't.
Well, this is illustrative of why they won't. Okay? These could be curves that fit the differential equation, and they're different curves, but they just happen to intersect at the 2 points of interest. Okay? Whereas if you have an initial value problem, it can't possibly work out that way.
This is the same as the line test. So.
The what?
Is this the same as the line test? It can't be a function?
It's not quite, because these are functions, but it's just that these two can intersect at the same 2 points, but not be the same solution. So therefore, it's not a unique solution. They have those 2 solutions perfectly fine, but they're not unique. Initial value problems, they guarantee, as long as they're contingent, all the things, conditions are met, they will work. Boundary value problems do not guarantee unique solutions. That's the whole point. We really do very little with them after this, just to introduce them to you.
Well, I was reading something. A lot of guys got pieces of this boundary problems. I mean, dissertations of boundary problems.
Right. And
Well, if they don't guarantee uniqueness and so forth,
right.
What are they doing? These things?
Well, here's the thing. I'm trying to think if you just may have to have more conditions to then make sure that you're unique. But 2 will not do for you. And there may be other, this almost sounds the same, but other constraints, like this, I could easily see you could have some that wouldn't be, but that your solution has to be increasing at A, not decreasing. If that's the case, that rules out the red line, that makes it the blue line. So maybe 1 or 2 other constraints may then give you a unique solution. But they don't go into this, so I don't want to say that, but that to me would be a possibility. Now, if you include all these possibilities here, again, this gets really murky seeming, and I haven't been able to convince myself this is valid, but they say it is. They say all these boundary values put together, boundary conditions put together, can be expressed this way as a general boundary condition. And again, I can't guarantee this. I can't guarantee it all works. But here's what they say, that alpha 1 y of A plus beta 1 y of B, no, I'm sorry, y prime of A, okay, is equal to gamma 1 and alpha 2 y of B plus beta 2 y prime of at B is equal to gamma 2. Okay? It says, they say the 3 pairs, but I would think they would mean all 4 pairs, would do the special case of the general boundary conditions. But frankly, to me, these don't look like boundary conditions. Well, yeah, they sort of do. Yeah, I guess so. Because here the y and y prime are both at the same values, and what b, y and y prime are at different values here. But that's just one condition. This is the second condition. But this is only good for a second order, that you could combine these and have these two. Now, they still don't say whether this is unique or not. I don't think they are, but rather than having to write all those out, you could combine them like this. But, you know, this is just more confusing because it seems like now you have 6 variables in here. 2 alphas, 2 betas, and 2 gammas, okay? Not just the fixed points A and B. So I haven't, in my own mind, showed that that makes any sense at all, but they seem to think it does, okay? But this may answer part of what your previous question was, example 3, okay? In example 9 in section 1.1, way back there, we saw that the 2-parameter family of solutions of the differential equation x double prime plus 16x is equal to 0. 2-parameter family of solutions of that differential equation. X is equal to C1 cosine 4t plus C2 sine of 4t. Okay? That should be a solution. I don't know if you remember that far back, but it's pretty easy to verify this almost in your head. X prime would be minus C1 minus 4C1 sine 4t plus 4C2 cosine 4t. So x double prime would be minus 16C1 cosine 4t minus 16C2 sine 4t. And then if you put that here with a coefficient of 16 for both of those, 16C2, C1 and C2, and then put this here and just have the 16, yeah, that's going to add to 0. So that's obviously a solution for this. Okay, we did it back before, but it's still a solution. Okay, I think we also pointed out there's another solution. Okay, suppose we now wish to determine the solution of the equation that further satisfies these boundary conditions. X of 0, I believe it is equal to 0, and x of pi halves, I can't write, goodness gracious, is equal to 0. Okay, so let's plug in, if I can fix that so it's readable. Okay, something like that. I left off at a parentheses, I think, or I erased it by mistake. Okay, maybe that's what was wrong with the whole thing. Okay, that's a boundary condition. X at 0 is 0, X at pi halves is 0. Not an initial condition because it's 2 different points. Well, let's plug in and see what we get. X of 0, in other words, when t is equal to 0, is equal to C1 cosine 0 plus C2 sine of 0. Okay? Well, what's sine of 0? 0. Okay? And by the way, this is equal to 0. X of 0 is equal to 0. So that tells you, and cosine of 0 is 1, so this implies that C1 has to be 0. Okay? By that? Okay. Now with that the case, we have X is equal to C2 sine of 4t. Okay? And let's do X at pi halves is equal to C2 times the sine of, second?
You say, okay, that's 4t, but that's just going to be 2t.
2 pi. 2 pi. And that has to be 0. Well, guess what? Sine is always 0. Sin of 2 pi is always 0. So that doesn't specify what C2 is. C2 could be any value in the world, and that would still meet those 2 boundary conditions. As long as C1 is 0, C2 could be any value, and these 2 conditions would be met. Okay? And this is an illustration of that. C1 has C at 0, or X at 0 has to be 0, and X at pi halves, which is over here, has to be 0. Okay? And you can draw a whole bunch of sine curves in there, and combinations of sine and cosine curves that both of those will meet. Well, actually, no, you only have sine curves. Any C2 you put in there, any C2 you put in there is going to give you a curve that goes through both of those points. Okay? And they happen also to go through.
Question.
Yes.
This is saying you just had to go through those 2 points. It doesn't matter about the shape or anything like that. Because suppose I want to make that interval, say, just pi. You would still go through pi half 0.
Yeah. The only, I think I see what you're saying. If you restrict the interval of t, still all these c values are still going to give you lines that go through that point right there. Okay? So limiting your t isn't going to, your interval of t isn't going to help either, because all these things will still go through those 2 points. So they just give you a sampling of them, but there's an infinite number. Any C2 you put in there is going to go through those 2 points. Any C2. Even C2 equals 0. There'll be a flat line, and it goes through both points. That was the one they pointed out before. This has infinitely many solutions. Okay? Now that's with your boundary conditions being at x equal at zeros. Okay. Now the B part here says, what if the boundary condition in that problem was changed to, same problem, but we're just going to change the boundary condition. So give me a different color. Make up a color here. Red. Okay, let's do red. Now we're going to change our boundary conditions to be x at 0 is equal to 0. But now we're going to say x at pi eighths equals 0. Okay. Now, you come up with the same deal there, but let's plug in x of 0 is equal to 0. So this will be x at 0 is equal to C1 cosine of 4, well, cosine of 0. Okay, plus C2 sine of 0, okay, and that's supposed to equal 0. Well, sine of 0 is always 0, always. So that's out of the picture here, and now you've got, and cosine of 0 is 1, so you got C1 is equal to 0, just like we got before, okay? So let's put the second boundary condition in there. X of pi eighths is equal to, C1 is 0, so that's out of there, C2 sine of pi eighths times 4 is pi halves. And that's got to equal 0. The sine of pi halves is always 1. So that means C2 also has to be 0. Okay? Well, that's not a very interesting problem, is it? We got x is equal to 0. Well, of course, that's going to work because it goes through the origin everywhere, but that is a unique solution. That's the only solution that will fit those boundary conditions. The only one. Okay? So that has a unique solution. It's the trivial solution. Okay? Now, I'm running out of room, so I think what I'll do is go back and erase everything but our setup up here. Ooh, yeah, I think I'm okay. One of these days it will all erase it. There, it did. Okay, pick me a color here.
Yeah, blue.
Blue, okay. We have a light, a medium, and a dark. Want just blue? Okay, that's the medium one. Okay, yeah. Same differential equation, same solution, but this time we're going to go with x of 0 is equal to 0. That's the same, nothing changed there. And x of pi halves is equal to 1. Okay, there was nothing that required those two to be the same, so that can be 1. Those are two boundary values. All right, let's plug in the first. X of 0 is equal, just like we had before, C1 times the cosine of 0 plus C2 times the sine of 0. Okay, and that's supposed to equal 0. That's our first condition. Okay, well, cosine of 0 is 1, so you got here C1 plus, but sine of 0 is always 0, so it doesn't matter what C2 is. C1 is equal to 0, just like we've had every time, okay? Just repeated it, so C1 is equal to 0. Got it. So let's do the second one. X of pi halves is equal to, C1 is 0, so don't worry about that, C2 times the sine of 4 times pi halves is 2 pi, right? And they claim that needs to be equal to 1. I'm sorry, equal to 1. I was looking at the 1 and wrote a 0. Okay, it's equal to 1. But wait a minute, folks. That can't happen either, can it? Because sine of 2 pi is always 0. And 0 can't equal 1. So this one has absolutely no solution. So you could have an infinite number of solutions depending on one boundary value. You could have a unique solution depending on another. And that may be where what you were saying, some certain problems do have boundary values and they do have unique solutions because you happen to be that one or that condition that they do work. This one would have no solution. No value will make that happen. None. 0, zilch. No solution.
So if we want to make it not work, all we have to do is find one condition that is not met, then there's no solution. If it doesn't meet precisely all of the conditions, constraints, whatever, then there's no solution.
Well, this one, if you say the x at 0 has to be 0, that's easy to fit. But when you say x of pi halves has to be something other than 0, you're going to have trouble, okay? Because there's no way you can make that work. Because if it was paired with the other, because the other one requires to C1 equals 0. Once you got that done, then you'll never get anything to make x of pi halves be anything other than 0. Then it will have a unique solution. Anything of pi halves, anything else will not work, period. Okay. So that may limit what your boundary values can be. All right. Now, again, we're talking terminology mostly. 4.1.2 is going to talk about another form of homogeneous or homogeneous equations. Earlier, we were saying, and I like the way they did right at the beginning of the section, they called them homogeneous in degree or something like that, or homogeneous in degree. Where was that? I thought that's such a clever way to say it. Why didn't they say that earlier? Having homogeneous or homogeneous coefficients. That's how they said it. Having homogeneous coefficients. Earlier they just called them homogeneous differential equations. They should have called them differential equations with homogeneous coefficients, meaning they all have the same degree. Now we're talking about homogeneous equations that doesn't matter what they're, it's a completely different thing. And here's what we mean by it. Remember our good old, I'm going back to black if it's okay. Okay? A linear nth order differential equation of this form. A sub n of x, the derivative, the nth derivative of y with respect to x to the nth power, plus a sub n minus 1 of x times the second derivative, n minus first derivative of y with respect to x to the n minus first, plus dot dot dot, plus a sub 1 of x dy dx plus a sub 0 of x y is equal to some, in this case, 0. Before, that was a g of x. Later we'll say the before thing was a non-homogeneous nth order linear differential equation. This is a homogeneous, meaning it's equal to 0. So we've changed the meaning of homogeneous. The other one was homogeneous coefficients. They all had the same degree. This one is homogeneous because it's equal to 0. Okay. that's said to be homogeneous, I can't talk, homogeneous or homogeneous, whereas the equation, if you put equal g of x, we would call that non-homogeneous or homogeneous, okay? So if you think back earlier, we had a 2y double prime plus 3y prime. Maybe we didn't have this one earlier. I was thinking we did. Minus 5y is equal to 0. What kind is that? Homogeneous or homogeneous. Exactly. Okay. How about this one? X cubed y triple prime plus 6y prime plus 10y. What's that?
Okay, go ahead.
Okay. Plus 10y is equal to e to the x. Non-homogeneous or homogeneous because it has a g of x out there that is not 0. Okay? Now, you might say, what's the big deal? And it's not a big deal until a little bit later, and then it's going to be a very big deal. Okay? So, but they're just dealing with us. Okay? And they mention here the word homogeneous or homogeneous in this context does not refer to the coefficients that are in our homogeneous functions, as in section 2.5. So they're just...
T to the n, factor out.
Yes, exactly. That's it. That was it. Okay. Now, if we were about to try to solve a linear third order or any order differential equation with a non-homogeneous, with a function of x at the end, you can't do it until you first solve this very same thing equals 0. And that's called the associated homogeneous or homogeneous equation to that. Actually, a little bit later on, yeah, I guess we'll still call it associated. But we start using all these adjectives for things, and it's so easy to get them confused. But this will be called the associated homogeneous equation or homogeneous equation for that one that was non-homogeneous. Okay. Now, it says in order to avoid needless repetition throughout the remainder of the text, we shall, as a matter of course, make the following important assumptions when stating definitions and theorems about linear equations like we have here. Okay? On some common interval I, here's what we're going to say. The coefficient functions a sub I of x for I all the way from 0 to n, and g of x are going to be continuous. We're going to make that assumption. We're not going to say it every time, but we're going to mean it every time. Okay? The second of these is that the a sub n of x cannot equal 0 for any x in the interval. It cannot equal 0 for any x in the interval. So we said that earlier, just to save time and space and keep from being repetition. We're going to assume that from now on. We're not going to always say it. So that still is there. Okay. I think we've just run out of time, haven't we? Okay. So we'll start next time. The bottom of page 121. I mean literally the bottom of the page. It's the thing called differential operators. Okay? And again, it's something they bring up, mention, and we hardly ever use again. We will occasionally throw them in there, but they're going to do it. And then we'll talk about differential equations, superposition principle, which we'll use over and over again. Linear dependence and independence, we'll use over and over again. And then we'll talk some about solutions of differential equations and come up with a test that we will use pretty frequently, not as often as you would think, but we will use some. And then we come back to non-homogeneous or homogeneous equations. That's 4.1.3. This is a long section, okay? And we'll come up with, it's mostly terminology. Mostly terminology. And then 4.2, reduction of order, very short. And then we finally start solving differential equations in 4.3. Okay, we'll get there. But we got a bunch more of blah, blah, blah to get through first. Which is sort of necessary, blah, 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 because they are things that we will refer to repeatedly. So you got to know what they mean. Did you have a question?
I'm just too dumbfounded to even know if I have a question.
Oh, well, this sounds confusing. Once you start using it, it falls into place a lot better. I get really bored with these first sections of every one of these chapters, but I see the utility of them, but I just think they've got to be able to present them better than this. But it seems like you could pick them up as you went along and say, okay, time out here. You have to remember this, okay? Rather than boring you to tears with all this stuff, and then, okay, here, if you remember, we did this back then.
That's always my whole thing about this. It would take 2 or 3 words saying, do the Thomas trick, if you recall, and then
Right.
write it right out.
Right,
So
exactly.
Maybe I'm just too partial to Thomas.
Yeah. I don't know. There's just something, it seems like all the modern texts follow these same.
Same money, words.
Yeah, I don't know.
Count the words.
Yeah, I guess so. You may